Welcome to Lesson 6.6 Advanced Optimization Techniques Overview. This lesson is about production grade optimization, the kind of techniques that separate a model that trains on your workstation from one that's ready to deploy at scale. You'll cover mixed precision training across FP16, BF16, and FP8, memory efficient techniques like gradient checkpointing and CPU offloading, model compilation with torch.compile, and profile. By the end, you'll know how to combine all of these into a single training pipeline that extracts maximum performance from your hardware. Budget about 90 minutes. This one is dense, and it's worth taking your time. Learning objectives. Here's what you'll walk away with. You'll understand the practical trade-offs between FP16, BF16, and FP8 precision formats and know which to reach for on your hardware. You'll implement advanced gradient checkpointing, use CPU offloading to run models that exceed your VRAM, profile your training loop to find real bottlenecks, and compile your model with torch.compile for measurable speedups. Put it all together, and you're looking at a 1.5 to 2x improvement in both training and inference speed, not from any single trick, but from stacking optimizations intelligently. Precision deep dive. Before writing a single line of optimization code, you need to understand what you're actually trading when you change numeric precision. Think of it like audio quality. FP32 is lossless, uncompressed, maximum fidelity, maximum storage. FP16 and BF16 are high quality compressed formats, half the memory, 1.5 to 2x the speed, with negligible quality loss for most tasks. FP8 pushes further, cutting memory to 25% of FP32 with 2 to 3x the speed, but accuracy starts to matter more. INT8 is the most aggressive, 3 to 4x faster, but you're firmly in inference territory. The critical difference between FP16 and BF16. They both use 16 bits, but BF16 preserves the same numeric range as FP32 by keeping an 8-bit exponent. FP16 has a narrower range, which is why it needs loss scaling to stay numerically stable during training. Your Tesla P40 supports FP16 but not BF16. That's an architectural limitation of pre-Ampere GPUs, and it shapes every precision decision in this lesson. FP16 allocates its 16 bits as follows: 1 bit for the sign, 5 bits for the exponent, and 10 bits for the mantissa. That 5-bit exponent is the constraint to understand. It limits the representable range to roughly plus or minus 65,000. Numbers outside that range overflow to infinity or underflow to 0, which is exactly why gradient loss scaling exists. The 10-bit mantissa gives you about 3 significant decimal digits of precision, more than enough for weight updates, but tight enough that you need to be deliberate about where FP16 is applied in your pipeline. BF16 takes a different design philosophy. It keeps the full 8-bit exponent from FP32, which preserves that wide dynamic range of roughly plus or minus 3.4 times 10 to the 38th. The trade-off is a 7-bit mantissa, less fractional precision than FP16, but far less prone to overflow or underflow during training. That's why BF16 has become the default training format on Ampere and newer architectures. It's numerically safer than FP16 without needing loss scaling. On your P40, this format isn't available, but understanding why BF16 exists helps you appreciate exactly what loss scaling is compensating for when you use FP16. The bottom line for your setup: use FP16. BF16 requires Ampere or newer, and the Tesla P40 predates that architecture. FP16 with proper loss scaling gives you the same memory and speed benefits. You just need to make sure loss scaling is active, which the Transformers trainer handles automatically. Technique 1. Mixed precision training. Mixed precision training doesn't mean the entire model runs in FP16. It means the framework is smart about where each precision is appropriate. FP16 for forward passes and matrix multiplications where speed matters most. FP32 for loss computation and gradient accumulation where numerical stability is critical. You get the speed of FP16 without sacrificing the stability of FP32 where it counts. Enabling mixed precision in the transformers trainer is a single argument. Set FP16 to true inside your training arguments. The output _dir tells the trainer where to save checkpoints and logs. The per_device_train_batch_size controls how many samples hit the GPU at once. This directly affects both memory usage and training throughput. The learning_rate of 2E4 is a solid. Once FP16 is set, the trainer handles everything automatically. It wraps forward passes in AutoCast, maintains a master copy of weights in FP32, and manages the loss scaler internally. You don't need to touch any of that machinery directly. The practical impact of mixed precision: training runs 1.5 to 2x faster, memory consumption drops by roughly 50%, and model quality is essentially unchanged. The automatic loss scaling is the piece that makes this safe. It detects when gradients are about to underflow and scales the loss upward before backpropagation, then unscales before the optimizer step. That mechanism is what lets FP16 training be stable without manual intervention. When you need finer control than the trainer provides, you can implement mixed precision manually with PyTorch's native tools. The model moves to the GPU first. The Adam W optimizer is initialized at a learning rate of 2E4. Then a grad scaler is created. This is the object that manages loss scaling throughout training. Inside the loop, each batch transfers to the GPU, and the forward pass runs inside a torch.autocast context with device type set to CUDA. That context is what triggers FP16 computation for eligible operations. After computing the loss, you zero the gradients, then call scaler.scale.loss backward. This applies the scaling factor before gradients flow backward. Before clipping, scaler.unscaler_optimizer restores gradients to their true magnitude so the clip norm is meaningful. Then scaler.stepOpere executes the parameter update, and scaler.updateACO adjusts. This pattern gives you complete control over the mixed precision pipeline when you need it. Loss scaling is the mechanism that keeps FP16 training numerically stable. Gradients in neural networks are often very small enough that FP16's limited range rounds them to 0 before they can update any weights. The scaler multiplies the loss by a large factor before backpropagation, which pushes those tiny gradient values into a range FP16 can represent. After the backward pass, the scaler divides them back down before the optimizer sees them. If the scaler detects overflow, a sign the scale factor is too large, it skips that optimizer step and reduces the scale. Over time, it converges on a stable scale value automatically. Technique 2. Advanced Gradient Checkpointing. Fine in your Rio, Ashiva. Gradient checkpointing is a memory for compute trade. Without it, PyTorch stores every intermediate activation from the forward pass so it can use them during backpropagation. For a large model, that's an enormous amount of VRAM. Activations can easily dwarf the model weights themselves. Full checkpointing solves this by discarding all activations after the forward pass and recomputing them during the backward pass. Memory drops dramatically, but training time increases because you're essentially running part of the forward pass twice. Selective checkpointing finds the middle ground. Checkpoint only the expensive layers, typically the attention blocks, and let cheaper operations recompute for free. You get most of the memory savings with a much smaller speed penalty. For your P40 setup, selective checkpointing is usually the right default. The selective _checkpoint_forward function iterates through a model's layers and applies torch.utils.checkpoint.checkpoint every n layers controlled by the checkpoint underscore. When a layer's index is divisible by that value, its forward pass is wrapped in a checkpoint call, meaning activations won't be stored and PyTorch will recompute them during backpropagation. Other layers run normally and retain their activations. The second half of this snippet shows how unsloth integrates with this pattern, passing unsloth as the use_gradient_checkpointing argument to get_peft_model activates unsloth's own optimized checkpointing implementation. In most cases, unsloth's built-in checkpointing is the right choice. You'd reach for the manual selective approach only if you have specific layer-by-layer requirements. Unsloth's gradient checkpointing is already highly optimized for the models it supports. That said, you can customize the checkpointing granularity when you need tighter control over the memory speed trade-off. This customization works by iterating through the model's transformer layers and enabling gradient checkpointing selectively here every fourth layer. The critical prerequisite is setting model.config.use underscore. The KV cache and gradient checkpointing are fundamentally incompatible. The cache stores intermediate key value states to avoid recomputation, which is exactly what checkpointing is designed to discard. Leaving use_cache enabled while checkpointing is active will either produce incorrect gradients or raise an error. After running this code, you won't see any terminal output, but you can verify the configuration by inspecting the gradient_checkpointing attribute on individual layers. The memory reduction shows up when you start training and watch VRAM utilization. Technique 3. CPU offloading. CPU offloading is the technique you reach for when a model simply won't fit in VRAM, even with quantization and gradient checkpointing active. The idea is to treat CPU RAM as a slow extension of GPU memory layers that aren't currently needed for computation live in system RAM, and only the active layers are resident on the GPU at any given moment. The execution pattern works like this. A small number of layers stay on the GPU permanently. These are the ones actively computing. The rest sit in CPU RAM, consuming no VRAM. As the forward pass progresses layer by layer, each layer transfers from CPU to GPU just before it's needed, computes, then transfers back. The GPU is never idle, but it's also never holding more than a fraction of the model at once. The cost is real. PCIe bandwidth between CPU and GPU is orders of magnitude slower than on-device memory bandwidth, which is why CPU offloading typically adds a 2 to 3x training time penalty. It's a tool for when you have no other option, not a general purpose speedup. The most robust way to implement CPU offloading is through Deep Speed 0 Stage 3. This configuration partitions optimizer states, gradients, and model parameters across all available devices, including CPU RAM. The 0_optimization block sets stage to 3, then configures offload_optimizer and offload_param to target the CPU. The overlap_com flag allows gradient communication to overlap. The contiguous_gradients flag packs gradient tensors into contiguous memory, reducing fragmentation and improving transfer efficiency. This configuration is saved as a JSON file that training arguments references via the deep. When training starts, you'll see deep speed's initialization output confirming which stage is active and how parameters are distributed. Watch for the per device parameter count in that output. It confirms offloading is working. The practical scope of CPU offloading on your hardware. A single Tesla P40 with 24 GB of VRAM can run 7B to 13B parameter models with this technique active. With both P40S and Deep Speed 0 Stage 3, you can push into the 30B plus range. The 2 to 3x training slowdown is the honest cost. If your model fits in VRAM without offloading, which covers most 3B to 7B models on a P40 with 4-bit quantization, don't use it. The transfer overhead isn't worth paying when you don't have to. Technique 4. Model compilation. Torch.compile is PyTorch 2.0 quote S answer to a long-standing inefficiency, Python's interpreter overhead. Every time a PyTorch operation runs, there's overhead from Python function calls operated for a model with hundreds of layers running thousands of steps. That overhead adds up. Torch.compile analyzes your model's computation graph ahead of time, fuses operations that can be combined into a single kernel, and generates optimized CUDA code that bypasses much of the Python overhead entirely. The result is faster execution without changing a single line of your model architecture. Compilation is a one-line change. Wrap your model with torch.compile ACIA before passing it to the trainer. The mode argument controls the optimization strategy. Reduce overhead is the right choice for training. It minimizes Python interpreter overhead with moderate compilation time. Default is more conservative. Max Auto Tune is reserved for inference, where you can afford a longer upfront compilation cost in exchange for maximum throughput. The full graph argument tells the compiler whether to attempt compiling the entire model as a single graph. Setting it to false is safer. It falls back gracefully when it encounters unsupported operations. Once compilation finishes, you'll see the confirmation message, and from that point the trainer uses the compiled model transparently. Expect a 10 to 30% training speedup on your P40 setup. The 3 compilation modes serve different purposes. Default balances compilation time against runtime improvement, a reasonable starting point if you're unsure. Reduce overhead specifically targets the Python dispatch overhead that dominates training loops, making it the best choice for fine-tuning. Max Auto Tune runs an exhaustive search for the optimal kernel configurations, which can take several minutes but produces the fastest possible inference throughput. For training on your P40, reduce overhead is the right call. Switch to Max Auto Tune when you are preparing a model for deployment, and inference latency is the metric that matters. For inference optimization, Max Auto Tune with full graph equals sign true is the target configuration. The full graph flag enables whole graph compilation, which allows the compiler to make optimizations that span operation boundaries, something it can't do when the graph is fragmented. The warm-up loop is not optional. Torch.compile works by tracing execution on the first few runs and compiling from those traces. Running 3 warm-up iterations before benchmarking ensures you're measuring compile performance, not compilation overhead. After warm-up, the timing loop runs 100 generation calls and reports average latency. That number is your ground truth for whether compilation delivered the expected improvement on your specific model and hardware combination. For inference, Max Auto Tune with full graph compilation typically delivers 20 to 40% faster generation compared to an uncompiled model. The exact improvement depends on model architecture and sequence length. Attention-heavy models tend to benefit more because there's more opportunity for kernel fusion in the attention computation. Technique 5. Profiling and bottleneck analysis. Optimization without profiling is guesswork. PyTorch's built-in profiler gives you a precise operation-level breakdown of where time and memory are actually going during training. The Profile Context Manager is configured to trace both CPU and CUDA activity, record tensor shapes, and track memory allocations. Each of these adds some overhead, so profiling is meant for analysis runs, not production training. The record underscore function context inside the loop labels the training step in the trace output. making it easy to isolate in the results. Profiling is limited to the first 10 batches here. That's enough to get statistically meaningful data without generating an unmanageable trace file. After the profiling block, key averages dot table sorted by CUDA total time shows you exactly which operations are consuming the most GPU time. That table is where you look first. The JSON export feeds directly into Chrome's tracing viewer at Chrome/tracing, giving you a visual timeline of every operation, invaluable for spotting unexpected serialization or idle periods. When reading the profiler output, 4 patterns signal optimization opportunities. Any single operation consuming more than 10% of total CUDA time is a hotspot worth investigating. It's either a candidate for a fused kernel or a sign that you're doing redundant computation. Memory allocation spikes that correlate with out-of-memory errors point directly at where to apply checkpointing or reduce batch size. CPU to GPU data transfers appearing in the CUDA timeline indicate that tensors are being moved during the forward pass, a sign that your dart loader or preprocessing pipeline isn't keeping the GPU fed. And a large number of very short kernel launches signals that operations aren't being fused, which is exactly what torch.com pile addresses. This memory profiling function isolates exactly how much VRAM the forward and backward passes each consume. It starts by calling reset underscore peak underscore memory underscore stats and empty underscore cache to zero out PyTorch's memory tracking and release any cached allocations, ensuring that the baseline memory reading before the forward pass gives you the model's static footprint. After the forward pass, the delta tells you the activation memory cost, how much VRAM your batch size and sequence length are consuming just to run the model forward. The backward pass delta on top of that is the gradient memory cost. The peak memory reading at the end captures the maximum simultaneous VRAM usage across the entire operation, which is the number that determines whether you'll hit an out-of-memory error. All values are reported in gigabytes, giving you concrete numbers to compare against your P40's 24 GB capacity. Combining all optimizations. This is where everything comes together. The pipeline starts by loading the model with 4-bit quantization via QLoRa. That's your memory foundation. Unslots get underscore peft underscore model call, adds LoRa adapters, and activates optimized gradient checkpointing in a single step. Torch.com pile wraps the model with reduce overhead mode before training begins. If both P40S are visible to PyTorch, data parallel distributes batches across them automatically. The training arguments configure FP16 mixed precision and 8-bit AdamW optimizer via optim AdamW underscore 8-bit gradient accumulation to simulate larger effective batch sizes, and the custom optimized trainer subclass adds per step timing to the training loop, so you have a running record of throughput throughout training. After training completes, the inference benchmark measures average generation latency and tokens per second, giving you a concrete before and after comparison if you've been tracking baseline numbers. Each of these techniques delivers a modest improvement individually. Stacked together, the cumulative effect is 2 to 3x the performance of a naive training setup. Performance benchmarking framework. The performance benchmark class gives you a reusable, structured way to measure the 3 metrics that actually matter for production readiness: training throughput, inference latency, and peak memory usage. The benchmark underscore training method runs the model for a fixed number of steps and computes steps per second, a hardware-agnostic measure of training efficiency that you can compare across different optimization configurations. The benchmark underscore inference method uses torch.cuda.synchronize before and after generation to get wall clock accurate timing without the synchronize call CUDA's asynchronous execution. It reports both average latency per sample and tokens per second which are the two numbers inference engineers care about most. The benchmark_memory method wraps a training step with PyTorch's memory tracking to capture peak VRAM usage. The report method assembles all three into a single structured output. Run this before and after applying each optimization technique, and you'll have data-driven evidence of exactly what each change is worth on your specific hardware. Advanced Optimization Checklist. This checklist is your pre-flight verification before any serious training run. On the precision side, FP16 enabled, loss scaling active, mixed precision confirmed in your training arguments. On memory, 4-bit quantization loaded, Gradient checkpointing active with use_cache disabled, batch size tuned to stay within VRAM headroom, and CPU offloading configured if you're pushing past 7B parameters. On speed, torch.compile active with the right mode for your use case, both GPUs utilized if you're running multi-GPU, dayloader workers set appropriately, and the 8-bit optimizer in place. For profiling, at least one profiling run completed on your actual training data, memory peaks measured and documented, and bottlenecks addressed before committing to a full training run. For production, inference benchmarked with the compiled model, all optimizations tested end-to-end, and your configuration documented so you can reproduce results. Work through this list systematically and you'll catch the issues that would otherwise surface halfway through a multi-hour training run. Key takeaways. 7 things to carry forward from this lesson. FP16 gives you 1.5 to 2x faster training and 50% less memory on your Tesla P40. It's always on. Gradient checkpointing trades recomputation for memory, and Unsloss implementation is already optimized for the models you're working with. Torch.compile delivers 10 to 30% faster training with no architecture changes. It's a free win on PyTorch 2.0 and above. The 8-bit Adam-Walger optimizer cuts optimizer state memory with negligible impact on final model quality. 2P40S with data parallel or deep speed gets you close to 2x training throughput. Profile before you optimize. The bottleneck is rarely where you expect it. And when you stack all of these together, the cumulative speedup reaches 2 to 3x over a baseline training setup. That's the difference between a 12-hour training run and a 4-hour one. Module 6 complete. That's Module 6 finished. You've covered the full advanced fine-tuning stack, multi-GPU training for 2 to 3x throughput, DPO alignment for safer and more helpful models, advanced LoRa variants including Dora, LoRa Plus and Ada LoRa, domain adaptation for building specialized expert models, custom architectures for problems that don't fit standard templates, and now production optimization that makes everything run faster and leaner. Each of these lessons built on the last. You're not just fine-tuning models, you're engineering the entire training pipeline. What's next? Module 6 is complete. The next step is putting everything you've learned into practice on real problems. Module 7 moves into real-world projects, end-to-end applications that combine dataset curation, fine-tuning, optimization, and deployment into complete production-ready systems. Everything from this module applies directly. Additional resources. For deeper reading on the techniques covered here, the original mixed precision training paper from Mikiewicz et al. Explains the theoretical foundation behind loss scaling and FP16 stability. The torch.compile documentation covers compilation modes and supported operations in detail. The PyTorch Profiler tutorial walks through interpreting trace output beyond what we covered here. The Deep Speed Zero paper explains the partitioning strategy behind stages 1 through 3, and the original gradient checkpointing paper by Chen et al. Is worth reading if you want to understand the memory compute trade-off mathematically. You now have both the conceptual understanding and the practical implementation skills to optimize LLM fine-tuning for production. That's not a beginner skill. That's the work of an experienced ML engineer. Flash attention addresses one of the most significant memory bottlenecks in transformer training. The standard attention mechanism scales quadratically with sequence length in both memory and compute. This chart shows that gap clearly. Standard attention's memory usage climbs steeply as sequence length increases. Flash attention's memory usage grows far more slowly, staying manageable even at long context lengths. The speed chart tells a similar story. Flash attention's throughput advantage widens as sequences get longer because it avoids materializing the full attention matrix in high bandwidth memory. Instead, it tiles the computation to stay within fast on-chip SARAM. The practical implication for your setup. Flash attention lets you train on longer sequences without hitting VRAM limits, and it makes that training faster at the same time. It's one of the few optimizations that improves both metrics simultaneously. This diagram makes the memory impact of gradient checkpointing concrete. On the left, standard training stores activations for every layer. L1 through L8 all hold their intermediate values simultaneously, pushing memory usage toward 100% of available VRAM. On the right, checkpointing stores only selected layers activations, marked as SageByte, and recomputes the others during the backward pass. Memory usage drops to roughly 40%. The trade-off is real. Those recomputed layers run their forward pass twice, adding compute overhead. But for large models on memory-constrained hardware like the P40, that compute cost is almost always worth paying. The key insight is that you don't have to checkpoint every layer. Checkpointing only the expensive attention layers while letting cheaper operations recompute freely gives you most of the memory savings with a smaller speed penalty. This comparison puts the precision format trade-offs in visual terms. FP32 anchors the left, maximum memory, baseline speed, no NAND risk. FP16 and BF16 both cut memory in half and deliver substantial speed improvements, but their ANN risk profiles differ. FP16's limited dynamic range makes overflow more likely without loss scaling, while BF16's wider exponent range makes it inherently more stable. FP8 pushes the memory and speed advantages further, but NAND risk becomes a genuine concern that requires careful monitoring. The practical read for your setup. FP16 with loss scaling is your target. It delivers the same memory and speed benefits as BF16 on hardware that supports it. You just need the loss scaler active to manage the narrower dynamic range. The transformers trainer handles that automatically when FP16 is set to true. This chart shows how memory optimization techniques stack. FP32 is the baseline, the tallest bar representing full memory consumption. Switching to BF16 cuts that roughly in half. Adding gradient checkpointing reduces it further. Combining QLoRa with flash attention and an 8-bit optimizer brings VRAM requirements down to a fraction of the FP32 baseline. The takeaway isn't just that each technique helps individually, it's that they compose. Each optimization targets a different source of memory consumption. Quantization reduces parameter storage, gradient checkpointing reduces activation storage, 8-bit optimizers reduce optimizer state storage, and flash attention reduces the memory cost of attention. Stack them all, and you can run models on your P40 that would otherwise require hardware with 2 or 3 times the VRAM. This visualization shows the activation checkpointing trade-off across transformer depths. The pink area represents standard VRAM usage. It grows steeply as you add layers, because every layer's activations accumulate in memory simultaneously. The green area shows checkpointed VRAM usage. It grows much more slowly, because activations are discarded after each checkpoint boundary and recomputed on demand. The bar chart on the right quantifies the cost. Some compute overhead is added, but the VRAM reduction is substantially larger. For deep models, which is exactly what you're fine-tuning, this trade-off becomes increasingly favorable as layer count grows. The deeper the model, the more activations accumulate and the more checkpointing saves relative to what it costs. This precision ladder organizes every format you'll encounter in LLM fine-tuning, from FP32 at the top down to INT4 and NF4 at the bottom. The GPU support column is the one to read carefully for your hardware. FP32 runs everywhere. FP16 runs on your P40. BF16 requires Ampere or newer, not available on the P40. FP8E4M3 is H100 specific. INT8 is available on INT4 and NF4 are software-implemented quantization formats available through bits and bytes regardless of GPU generation. NF4 is specifically what QLoRa uses for its 4. The use case column maps each format to where it belongs in a production pipeline. FP32 for reference and CPU work, FP16 for training on your setup, INT8 for inference quantization, NF4 for QLoRa fine-tuning. Match the format to the task and the hardware, and you'll avoid the precision-related failures that trip up most people new to this space. This throughput map gives you a ranked view of what each optimization actually delivers. The numbers are worth internalizing. Removing padding with data collator for seek to seek set to not pad is the highest single technique gain at 40%. It eliminates the wasted computation on padding tokens that would otherwise consume GPU cycles without contributing to learning. Increasing batch size delivers 35% if your VRAM allows it, because larger batches improve GPU utilization. Flash attention to adds 30% and requires no configuration beyond installation. BF16 training, when your hardware supports it, adds 20%. Gradient checkpointing costs 20% in speed, but that's the price of the memory headroom it creates. Torch.compile adds 15% on PyTorch 2.0 and above. DeepSpeed 02 adds 10% through more efficient gradient communication. Setting num_workers above 0 in your DLORA adds another 10% by keeping the GPU fed during data loading. The cumulative effect of applying all of these simultaneously is what gets you to the 2 to 3x total speedup cited throughout this lesson.